Good morning. We are back, and we're actually moving on to another chapter. So we'd gone through chapter 1. We said don't worry so much about chapter 1. Definitely take a look at the homework problems. Definitely think about the ideas of units conversion, really important from chapter 1, and kind of think about estimating numbers and what that means. I promised a lot when I was presenting chapter 1, that once we got into chapter 2, we would start looking at problems that looked much more like the types of problems that we'll really encounter in this course, so I'd better make good on my promise. Chapter 2 is starting to look at motion. Now by motion, let's see, we've got an automobile here. Ooh, it's got a parachute on the back. And there's something called velocity, which is going to tell us how fast the car is moving. There's also something listed there as acceleration. And acceleration tells us about how velocity maybe is increasing or decreasing. Anytime the velocity is increasing or decreasing, that's an acceleration. And so we've got arrows keeping track of that. This is the kind of stuff we're going to be working on in the chapter, going in and determining what are accelerations, how are they calculated, what are velocities, how do we calculate those. And this topic of motion we refer to as kinematics. Now if you were talking to your friends and your friends said, hey, what are you doing in physics this first week, and you told them that we're studying motion, they would think, well, that sounds boring, motion, huh? Ooh, but if you tell them we're doing kinematics, they're going to be impressed. They're going to go, wow, kinematics. So anyway, that's just our word that we use for the study of mathematically describing motion. And that's what we're going to do here. So yeah, let's get started with this. This is the real stuff. So here, I think I suggested that here you really need to know what's going on, and if it's not making sense, stop by office hours, let me know what questions are coming up, because this stuff you really want to understand as we go through. Don't fall behind in the course, stay caught up, and that means staying caught up with everything we talk about in chapter 2. So again, the slides are going to start with a list of topics. This is mostly for you when you're going back through. I just want to see a list of all the topics in one place, but I can already kind of see here velocity, acceleration. I think we're in the right place. Ooh, here it says integral calculus, and ooh, we won't worry about that right now. So here we are, starting out in chapter 2, and it's looking at something called reference frames and displacement. So any measurement of distances. So there's a number of words we use to talk about distance. First of all, we talk about distance between points, and then we talk about the length of things. That's also a distance. And then we also are going to talk about, in physics here, we're going to talk about something called displacement, and we'll talk more about specifically what we mean by displacement. But as far as reference frames, you may be familiar that if we have someone on the train carrying out some kind of a measurement of something, it could be different from somebody outside the train. So for example, if you're on the train sitting there, you might decide to just say, hey, I'm at rest. It's a smooth track, we're headed in a straight line, and as far as I can tell, I'm at rest. It feels like I'm at rest. And it turns out that objects that are maintaining a perfectly constant velocity, everything is equivalent to just being at rest. There's really no difference between what we consider something at rest versus something moving at a constant velocity. We'll look at more situations. By that, what we mean is if these people are sitting here, there's nothing they have to do to take into to compensate for the velocity of the train if, again, the train's on a perfectly smooth track, traveling at a perfectly constant speed. I mean, a more extreme example of this is flying in an airplane. If you're flying in an airplane at, 700-800 kilometers per hour, 500 or 600 miles an hour, if it's a smooth flight and you're maintaining a constant speed, you get up and you walk back and forth in the aisle, and you get out in the aisles and play catch, and it's just as if you're at rest. the physics of a constantly moving reference frame is the same as a reference frame at rest on the surface of the Earth. And as you know, saying, well, the surface of the Earth, that's kind of a reference frame it's not moving, it's fixed, it's still, but we know that's not true, right? The orbital speed of the Earth is 67,000 miles an hour. And you would think, well, hey, if I was moving 67,000 miles an hour, I would know that, right? Apparently you don't. So again, the way that nature works, the way that physics works, is that if you're in a reference frame that's moving in a straight line, in a very smooth fashion, there's no bumpiness going on, so you're just maintaining straight line motion, doesn't matter how fast you're traveling, it feels like you're at rest. Now what these people are noticing is that this person got up and they're walking along the train, and so they look up and they could measure from within the reference frame of the train how fast is this person moving. They could measure the distance and they could time that, and they could find out, oh, that person has a speed of 3 meters per second, 2 meters per second walking along the train. So they could come up with a measurement within the train. Now, someone standing outside the train would measure something different, because a person standing outside the train would observe the people sitting within the train as already moving at some speed. Maybe the train's moving at 30 meters per second, which was 67 miles an hour. So let's say the train's moving at 30 meters per second. This person gets up and walks at 2 meters per second relative to the train. Well, the person outside is going to see that 2 meters, an additional 30 meters per second added on. They're going to see this as a faster speed. Now, this introduces the idea of different reference frames. And within a reference frame, moving at constant velocity, all the formulas for physics are going to work the same way. We can carry out what we're going to affectionately call velocity addition. You just add or subtract speeds, and that will take care of any differences of velocity that are being measured. So we'll come back to this idea of a reference frame. Now, kind of built into the idea of a reference frame is you can mentally impose a coordinate system. So we could come up with a coordinate system. Now, coordinate systems are for our convenience. So when we're working within a reference frame, the coordinate system allows us to specify where different things are located and where different things are moving. So in here, we're going to make a difference between, we're going to specify what we mean by displacement. Displacement, let's take a look at this. Let's say that we're working within some reference frame, and it can be the surface of the Earth. So let's say that it's just someplace on the surface of the Earth, and we've mapped out different distances. And what happens is that we walk 70 meters in some direction. That takes us 70 meters away from what we've defined as the origin of our coordinate system. Now, once we get 70 meters away, then we stop and we go, I actually want to go back to that thing that we saw earlier. So we walk out 70 meters, and you guys are all imagining how far 70 meters is, right? Okay, good. So 100 meters is like a soccer field, okay, or a football field, something like that. So 70 meters would be, 70 meters, 70 meters of that. And so we walk out 70 meters and we come back 30 meters. How far have we traveled? And you go, well, the distance that I walked 100 meters, right? I get credit for walking 100 meters because I walked out 70 and 30. But mathematically, what's the position that we're at now? And you would say the position that you're at has a displacement from the original starting location of 40 meters. Okay, so the displacement for that journey that this person went on is 40 meters. The net difference, just looking at the starting point and the final point, measuring distance that way, would only be 40 meters of displacement, even though the person traveled a distance of 100 meters. Now another thing I want to state one more time is we get to decide what the coordinate systems look like in a problem, and that's one of the skills in physics that you want to develop is in what way can I define the coordinate system that will make solving this problem as often we want to think as easy as possible, but maybe a better way to think about it is as insightful as possible. So I want to define a coordinate system that makes sense kind of, when I'm setting up these mental diagrams, when I'm drawing my diagram, maybe I want to pick a coordinate system that will help me think about the physics most carefully. So for whatever reason, I think it's a good choice, they picked 0 as the starting point. Hey, why not, right? If the person's going to walk out and walk back, why not just have their starting point be called 0, and then all the displacements will be easier to calculate. But we didn't have to. We could have shifted the coordinate system so the origin was over here somewhere. Now the other item that we should talk about here is we've got x here, we've got y, apparently there's going to be a z direction. Now, for the purposes of this chapter, if you look at the title, we're only working in one dimension. So we're going to learn everything in sticking with just kind of one dimension, and then in chapter 3 we'll move on to 3 dimensions and start looking at more complicated motion. So for right now, everything's happening along. We really only need one axis to work from. But that's the idea of displacement. Now mathematically, the way we can write displacement is we can say that it's a difference between the one position and another. So so we use the symbol delta. So I do want to say a few things about using delta on these two. Delta x indicates that there were 2 x measurements, presumably, and that we're taking the difference between those. So a lot of times, and that's fine, the delta gets referred to as change in, this is the change in x. And that's fine as long as you stop and think about what you mean when you're telling yourself this is change in. I always like to think of this as, a delta x is a difference between the positions of 2. I guess I think more in terms of difference, and thinking in terms of change in is fine as long as you know what that means. Okay, so here we've got, again, we've set up a coordinate system, and we had something that started at position x1, and that happened to be at the 10-meter mark on our coordinate system that we set up. And then the x2 location is at the 30-meter mark, and presumably something moved from position x1 to position x2. So the delta x, or the change in x, or the difference in x that we observe, there is a difference of 20 meters. Okay, and we got that by taking the 30 and dividing through by the 10. Now, here, the displacement is positive. The reason the displacement is positive is because that's the way we set up our coordinate system. Now, typically, almost always, we set up coordinate systems in a way where the value of x is increasing when we go from left to right. But we wouldn't have to do that. Okay, so we could have used a reversed coordinate system here. It happens that we're calling this the positive direction and this the negative direction. And that's why this displacement is positive 20 meters, whereas going in the opposite direction gets listed as negative 20 meters of displacement. Okay, it has to do with the way the coordinate system was set up. So there's nothing inherently positive about this motion or inherently negative about that one, right? So we'll see more examples of working from that. Now, speed, let's move on. We've talked about displacement. Speed is the distance something travels, or the displacement actually, during a given time interval. So on average, when we calculate an average speed, if we look at distance traveled, so here we actually are going back to just distance, during time elapsed. So we have to decide when are we going to be working in terms of distance versus displacement. So for right now, they're calling average speed in terms of distance. And this is a distinction that the textbook is going to make. I'm not going to be as strict about it. They're going to say when we use the word speed, we're thinking in terms of distance traveled, whereas with velocity, we're thinking of displacement. I'll try to stick with that, but if I'm not entirely consistent, I don't know if that's a serious problem or not. For the previous example, the total distance traveled was 100 meters divided by 20 seconds, and that's going to give us an average speed of 5 meters per second, whereas the average velocity is going to be the 40 meters divided by 20 seconds. That's only going to be 2 meters per second. Okay, so you kind of get the idea of whether we're working in terms of distances or whether we're going to be working in terms of displacements. Now, what that's going to be divided through by here is the time interval. How much time elapsed? What was the time interval between being at location 1 and being at location 2? And what they're saying in each case is 20 seconds. Now, that's probably not what happened here. So they're probably not both 20 seconds. Oh, they are both 20 seconds. I take that back, sorry. So it took 20 seconds to come out here and then come back to this location. Absolutely. So it was just one journey that was made. It's not two separate. Okay, so that makes sense, I hope. Questions on that? So I've got a lot of office hours. Don't hesitate to just, you don't have to, doesn't have to be, can be very informal. Just stop by the office hours and we'll get whatever questions you've got. You can come and go. It works fine. So if you have a quick question, stop by office hours and we can often get those answered pretty quickly. Get you unstuck. So here's another example. It says that as a function of time, we've set up an x-coordinate system to follow this person. They've gone from the 50-meter mark to the 30-meter mark. So we'll call this x1, we'll call this x2, and so we can calculate a delta x from that, and then it's going to all occur during a 3-second time interval. So I want to think of that as time interval. What was the runner's average velocity? So let's try that. So I'm going to say velocity. I know my V's and my R's can look the same. Sorry, I need to cross that out right there. So this is an average velocity, delta x divided by delta t. Now delta t is going to be a time interval, okay, and delta x is going to be a displacement. So it's a displacement divided by a time interval. I can write that as x2 minus x1. Now I could write this as t2 minus t1. So I did that. I called t1 0 seconds and t2 3 seconds. Anyway, the displacement worked out to be negative 19.5. And 3 seconds was the time interval. I can divide those. This says that the velocity, the average velocity, negative 6.50 meters per second. Now remember, the minus refers to the coordinate system that we had set up. So there's nothing inherently negative. It just happens to be negative because of the way the coordinate system was defined. That would be the average velocity. So let's take a look at the distance that a cyclist travels. It says a cyclist, how far can a cyclist travel in 2.5 hours if her average velocity is 18 kilometers per hour? Okay, so now this is the distance then should be given by the velocity times the time traveled, and in this case it's one-dimensional. Even though it's not a straight line, we can still kind of think of this as one-dimensional because the road curves back and forth, but we're just keeping track of distance. It's not displacement. So if we just follow the distance, then we can just add together the entire length of whatever path the bicyclist took. So let's start with this. Now I'm still using V, okay, even though strictly speaking, these are, I guess they're supposed to be speeds, average speeds instead of velocities. But the distance that we travel, the delta x, average speed times the time interval, that's 18 kilometers per hour for 2.5 hours. That's going to give me a total distance of 45 kilometers. Ooh, and I wrote displacement. Why did I do that? Okay, so oh, it's a straight road. It is. Okay, I was just going to say that only works. Those are only interchangeable. If the road was completely straight, it is. Don't worry about the curvy stuff that I talked about before. So we're going to say that there's a displacement, and that's 45 kilometers, and that's because the person found a road that was just straight for 45 kilometers, and there it is. There's the picture right there. x1 and x2, time 1 and time 2. We're able to go in and come up with those values. Okay, the delta x. Yeah, so I guess those are just formulas representing what's going on. We were able to actually calculate everything, not putting in the separate values of x1 and x2. So we work directly in terms of the deltas. All right, now average velocity is fine, but I'm guessing that, I mean, you guys have all taken calculus, and so you've probably looked at problems now in your calculus classes where things aren't moving at a constant speed. There's a variable speed going on. You probably, a good number of you probably have taken physics courses before too, where they've introduced formulas that have what we call instantaneous velocity. So what if we're not traveling at a constant speed? What if we're going a little faster sometimes and then we slow down, maybe we stop for lunch, we get back, we start traveling again. What we would like to do then is take shorter intervals of time. What we can do is we can break things up. Instead of taking the entire time that we were traveling, what we can do to get an instantaneous velocity is kind of take a measurement every second as to how fast we're going. And if we're using really short time intervals, we're going to call that dt. I hope that looks familiar from calculus. So when you take derivatives in calculus, what that really means, or one way to think about that conceptually, is you're taking a ratio of two different values. Taking a derivative is saying when variable t changes by a small amount, and we'll call that dt, how much does variable x change by? So dt represents a very, very short time interval, and dx represents a very, very short displacement. And the idea of taking a derivative says that during the time interval dt, there was a displacement of dx. Those two infinitesimal values are related to each other. During time dt, there was a displacement of dx. Okay, now the way that gets presented is in the limit, as the intervals of time get shorter and shorter, our delta x over delta t formula crosses over into dx divided by dt. So in the same way we can take a delta x and divide it by a delta t, we're essentially taking a dx and dividing it by a dt. Those are just really, really short displacements and time intervals. I know I'm repeating this over and over, and it's because, when I took calculus, I had kind of this idea of what taking a derivative meant, and I learned all the rules for taking derivatives of different functions. But then when I got into physics and started taking classes, I realized these can just be manipulated as if they're variables. dx and dt independent of each other, can be moved around in formulas, and we'll see a lot of examples for that. All right, so here's a speedometer. Now what they claim here is that speedometers are measuring your speed over short intervals of time, and I'm not sure if that's true. I mean, if you have a mechanical speedometer, if you have a speedometer which actually, as your wheels are going around, if there's a gear system set up or something where there's a cable that's turning around with the odometer, then that's instantaneous. You know, if I speed up a little bit, I slow down a little bit, that cable, the speed at which that cable's turning around is going to change, and that's going to show up as a difference in my speedometer. So I've always thought of speedometers as kind of an instantaneous velocity. The claim here is that it's actually just measured over a very short time period. I don't know which it is, so maybe some of you or many of you are more familiar with the inner workings of speedometers on cars these days. But potentially, and what they say, ideally, a speedometer should be giving us an instantaneous value. So that's going to be changing from one moment to the next. Now, we've made this definition of v is equal to the ratio of dx dt, and you're thinking, well, don't I need a function or something to work from? And in math classes you do, right? So in math classes they give you functions and you take derivatives and you find things out. In physics and engineering, when you're measuring something, we have to go in now and determine how we're going to get those numbers. And it's not that somebody gives you a formula. You know, a car zips down along, you've got a test track set up and you're racing a car around it. No one comes over and hands you a formula and says, here's the formula that is describing the motion of this car. You actually have to collect a lot of data. You have to go into the lab. You have to collect a lot of data on the car, and from that, you have to kind of try and develop your own formulas to describe the motion. Okay, so the math is great that we learn in calculus, but you have to realize that with, again, with these kind of measurements, we've got to collect a lot of data to understand what formulas might be describing the motion here. Anyway, here's a couple of graphs. Graphs are going to be great. They're our friends. I hope you enjoy working with graphs. I know a lot of students are hesitant about working with graphs, but graphs are a great way to show a lot of information quickly. It's also a way to catch errors that we've made in our thinking. So what we're saying here is, let's think of these two graphs. Here is the velocity in kilometers per hour. It's got units clearly labeled. Here is the time in hours or tenths of an hour. And what is this graph describing? And I go, hey, this is describing constant velocity. So the graph above is saying that whatever object we're following has a perfectly constant velocity. It just maintains the same speed and the same straight line direction. So try this. This could be like a take-home project for you. Practice moving with constant velocity. You know, pick a space, give yourself some space and go in a straight line and try and maintain a constant speed. You know, if someone says, hey, don't run into me, go, you got to move out of the way. I'm practicing constant velocity and I have to go in a straight line and I have to keep maintaining the very same speed, so make sure you have a clear path for that. The graph down below is probably something that occurs more commonly, where we go fast for a while and then maybe we slow down. So this is describing something that picks up speed, starts at rest. So we're starting at a velocity of 0. Notice in this graph, the object was already moving when the timer started. So when the timer started, this velocity was already at 40 kilometers per hour. So it's kind of like this car goes by at 40 kilometers per hour and we hit the timer as it goes past us. It's already moving. This time, you know, the car's starting out at rest and then it picks up speed, it accelerates up to 50 kilometers per hour, and then it goes 50 for a while and then it slows down, it decelerates, it accelerates in an opposite direction, and then it travels at 20 for a while. Now what they're claiming here is that the instantaneous speed always equals the magnitude of the instantaneous velocity. So however fast we're going at a given instant is giving us an idea of what the instantaneous velocity is. Now a way to check and compare these graphs, notice that on this graph the object is going at 40 kilometers per hour the entire time. You know, is the object described by the lower graph ever traveling at 40 kilometers per hour? and only for a brief instant here during an acceleration, and then here again as it's slowing down, it's traveling at 40. Now on this one, so the average velocity here is clearly 40. The average velocity here they're claiming is 30. We would have to go in and do some more careful calculations to verify that. One of the things I did want to bring in though is when we do these graphs, I'm going to say what you always want to do is look at the axes. Look at the axes of the graphs and be clear what's on the vertical axis, what's on the horizontal axis. Because if you're looking at a graph, you don't really know what it's telling you unless you look to see what it's telling you. Unless you look to see, this is talking about velocity, so that's what's being kept track of as a function of time. Now, if we do velocity as a function of time, you may remember this from your calculus classes, the area under the curve represents the distance that we've traveled. So if I took this 40 kilometer per hour velocity and I ran that for half an hour, if I do the area would be 40 kilometers per hour times 0.5 hours, that would give me 20 kilometers. And that would be the area under that graph. Now, the area under that is displacement if it's a v versus t graph. So we're going to see for all the graphs we look at, the area under the curve means something. And so that's something we want to keep track of. This one, calculating the area, determining the area under the curve, would be more difficult. Okay, so we would have to use different techniques to determine what the area is. But if we found the area, that would tell us how far the object has traveled. Okay, so here's kind of the same approach again. What we're going to do is, let's plot on a graph. Now they're calling these particles, but I'm going to call them objects. So I have an issue with textbooks referring to an object as a particle, and that's because I worked in particle physics research for years. So when I see a particle, it makes me think of an electron or a proton or a neutrino or something. And here by particle, they just mean an object. So in physics 4a, anyway, I'm gonna be using the word object instead. Now I mean an object that's small enough and concentrated enough, we can treat it as if it's all moving together as one object. And I don't know, an automobile works for that, right? So I can treat an automobile as an object and say that as a function of time, maybe it's traveling this path. Okay, so here is the position of the object. Here's its position at t1, it's at the location x1, and at t2, it's at position x2. Here are points. Over that range of time, over that interval of time, how could I come up with an average velocity? And an average velocity would say, hey, I just have to know the endpoints. I don't have to know the details of what happened in the middle here where it curved. If I know the endpoints are enough that I can calculate delta x, what was my displacement during that time, and I can calculate delta t, how much time interval are we talking about? So if I take the displacement and divide through by the time interval, delta x over delta t, that's going to give me an average. But notice how the average value doesn't get any of the instantaneous velocities right. If I look at, well, this is an x versus t graph. So if this is my function of x, as a function of t, and I don't have a mathematical formula, I just have collected a bunch of data. I've collected a bunch of data about this object, and I know exactly where it was located at each time, and I've plotted that. Well, the slope of the function at each point is going to be equal to dx dt. That's going to give me the instantaneous velocity. So this says at point 1, I do have a positive slope here. I am moving in what we've determined to be what we're calling the positive direction. And here I'm also moving in the positive direction, but notice the slope is steeper here. I'm increasing in x at a faster rate. And so here I'm going faster. If I do a tangent to that red line, than I am here doing a tangent, and this is kind of the average slope. So the average slope gives me the average velocity. But what we want to get to is dx dt, and that says that we have to start looking at shorter and shorter time intervals. And so what we do is we move, let's say we move point 2 to here, maybe we move it to here. At some point, I'm going to hit a tangent to that curve, and that will give me the instantaneous velocity. So this is going to be our definition for velocity. By definition, mathematical definition, instantaneous velocity, which is really just velocity. So we're going to typically drop the word instantaneous. When we say velocity, we're indicating velocity at a particular instant in time. And so velocity at any instant is given by dx dt at that instant. Okay. And it doesn't have to be a formula that I'm taking a derivative of. What I can do is collect a bunch of data, again. So I'm collecting a bunch of data. I draw a line through all that data to represent my best approximation to what actually took place in terms of displacement versus time. And then I'm getting out a ruler or something and finding out the tangent line. The tangent line is going to have a slope of dx dt, and that's my velocity. All right, here's an example. Instantaneous velocity. And here we have, it says we have a jet engine here. Okay, let me check back really quickly. So we have a jet engine here, and we're trying it out. So we've set up a rail system, and we're going to try out our jet engine. I hope they've planned for this. So here's the jet engine. It's taking off. And it says that we're going along an experimental track, so now I'm not sure if it's the jet engine or the track that's experimental. And what we're going to do is we're going to choose to call the length of the track our x-axis. And we're going to choose the direction of the jet engine's motion to be positive. That seems easier than defining it to be the negative direction. So, for convenience, that's what we'll do. Now it says that we're going to treat the engine as if it's just a compact object. I know they're calling it a particle. They're going to say this is an object we can treat as if it's just, we're treating it as if it's been located at one point. So we're keeping track of some point on the jet engine. It looks like this point right here. And we're following where that's located. Now here is a graph. So we collected a bunch of data on this. And we found out that at time t equals 0, we actually didn't start out at 0. That's kind of interesting they didn't do that. So the engine started off, maybe it's because of the way there, anyway. The engine's starting off right here, and then we can see that it's picking up speed. Now this is an x versus t graph. This is a displacement as a function of time. So different axes. On this one, it's the slope that's going to give us the velocity. So it's the same as the couple diagrams we saw before, but it's not the velocity versus time graph. This is x versus t. And so if we can get slopes at different times, we can figure out what the velocity is at that instant. Now they've collected a lot of data, and what they have found is that the position of this test jet engine as a function of time is well represented by the mathematical formula a t squared plus b, where a and b are constants that we've determined by analyzing the data. Okay, so we've analyzed a bunch of data. Maybe we've plotted it onto, we've entered this into some kind of a software package, and the software package is drawing a graph for us, or maybe we drew the graph ourselves. And then we're trying different mathematical functions to find out which one fits the data well. And we have found out that the function at squared plus b fits the data really well. And we have determined the value of a to be 2.10 and b to be 2.80. Now those have got to be in the right units. x is going to be in meters. So since x is in meters, it says that each term over here has to also be in meters. That says b's got to be in meters. And C it is, 2.80 meters. Now what about A? A itself is not going to be in meters because A needs to include meters, but it also needs to cancel out two factors of time. So A would need to have units of meters per second squared. And it says that the value here is 2.10 meters per second squared. And then it says during the displacement of the engine, during the time from T1, which is at the 3-second mark, up to the 5-second mark, we're supposed to find out the displacement. All right, so again, we've got this, displacement graphed. Now, just checking a period got left out there. I put the period in and put an arrow to it to emphasize that I had to put a period in. Okay, so here's my write-up. So I'm trying to solve this problem. So I'm starting off with what was given. So I want to organize everything. So I'm going to read carefully through the problem. I don't want to skip anything, and that's something I have to work at. You know, I often will try and skim a problem and hope that I'm getting all the information. So I've really got to remind myself as I go through, yeah, you got to read this carefully. So we've collected a bunch of data. They've come up with, this is a good example of a model, some kind of a mathematical formula that represents the data that we've collected. And so I'm going to work from my mathematical model now, and we've determined what the best fit constants are, and that's what's given. So using that formula, what I can do is I can go and plug in some different values. Now I plugged in 0 just because I was curious. And so using this, it says that at t equals 0, the jet engine was at the 2.80 mark as far as distance. So its starting point was not what we called 0. It's fine. It was, you know, the coordinate system was just set up a little differently. So it started out already here, and then at the 3-second mark, the jet engine was at the 21.7 meter location, and then at the 5-second mark it was at 55.3, and that's from using this formula. So now that I've got a formula that describes the data, then I can start working from the formula. It took up, you know, I spent a lot of time collecting the data and finding a formula that would work, and now I've got the formula, I'll work from the formula. So if I look at displacements, 21.7 and 55.3, what I can do is I can get an average velocity. Ooh, is that the first part? Oh, this is part A. So part A is looking at the displacement, and x1 and x2 I was able to determine. And so delta x, 33.6 meters. So how far did this jet engine travel specifically between the 3-second time and the 5-second time? During that 2-second time interval, how far did it travel? 33.6 meters. Well, then on average, if the displacement was 33.6 and the time interval for that was 2 seconds between 3 and 5, then the average speed was 16.8. But now what we want to do is we want to come back and determine right at the 5-second mark how fast were we traveling. Okay, so let's go back and just let me go back and check this. So we got the displacement, and then in part, we got that was part B that we did, huh? We got the average velocity. So we got the displacement, the average velocity. Part C is saying right at the 5-second time, what was the instantaneous velocity? Now to get the instantaneous velocity, we're going to take the function that we determined by analyzing our data. We're going to take a derivative of that. We're going to take dx with respect to dt, and using the rules that I've learned in my calculus class, that's going to be 2 times a times t I'm going to plug all those numbers in, and this tells us, this is a general formula for velocity, and you can see that as a function of time, the velocity is going up. The instantaneous velocity steadily is increasing. Now at the 5-second mark, I put in the value for 5 seconds, and what I ended up with was 21 meters per second. Okay. So the average velocity during that time was 16.8 meters per second, but clearly, since we're picking up speed right at the 5-second mark, we're going faster. We're going 21 meters per second. We could go back. We could have added, this would be a good exercise. We've got t at these different times. We've got x. How would we go in and solve for v at each of these different times? And we would just plug numbers into this formula. At t equals 0, the velocity is going to be 0. We're at this location, and right now we are at rest. At 3 seconds, can we do the math? 6, 12, 12.6, is that right? Possibly. 4.2, 12.3, maybe 12.3, something. So we could get the velocity for the 3-second mark, and we have plugged in the numbers and gotten the velocity for the 5-second mark. Okay. 4.2, yeah, 12.6, right? So 12.6 meters per second, and then at 5 seconds we're going even faster. So once we've got that formula, we can start plugging in. So as long as the formula is reliable, the numbers that we're calculating are going to be reliable. Okay, so we've talked about velocities, and we've talked about velocities going up and down. Acceleration, we're going to introduce this now. So let's see, we got displacement discussed. We've got velocities that we've looked at in a good amount of detail. Now we want to move on to acceleration. That's kind of the big three in this chapter. So the average acceleration comes from looking at how much the velocity has changed during a time interval. So again, we're thinking of a certain time interval, but now it's not how far we've traveled, it's how much has the velocity shifted. We started at this velocity, we ended up at a different velocity. How much did the velocity change during that time interval? So here's a car, and it's saying at time t equals 0 that it's at rest. It's not moving. But if it has an acceleration, let's say it has an acceleration of, we're going to give it a number here, it's going to be 5 meters per second squared. So that's the acceleration we're going to be working from here. That says that if it's 5 meters per second, then every second that goes by, it's going to be going faster by 5 meters per second. So after 1 second, it's going 5 meters per second. After 2 seconds, it's going to be 10. After 3 seconds, that's going to be 15, and then 20, and then 25. So by the time we've traveled for 5 seconds at that consistent, constant acceleration, we're going to be all the way to 25. Now the accelerations don't have to be constant. This is just an example that we're starting out with, saying what would happen if the speed increased at a steady rate. And so it says it accelerates along a straight road from rest to 90 kilometers per hour in 5 seconds. What's the average acceleration taking place? How did they determine that? So we can use the formula here, saying that the velocity, how much did the velocity go up? Well, it went from 0 to 90. Now the 90 kilometers per hour, I really don't want the acceleration in kilometers an hours. That's going to be awkward. So I'm going to convert back into meters and seconds. Meters and seconds are going to be much more useful to work with in terms of accelerations. So I'm first of all going to get my velocities, and I'm going to take that 90,000 or the 90 kilometers per hour and convert that. Now, one way you can convert kilometers per hour is pretty quickly. 90 kilometers is the same thing as 90,000 meters, right? So I can take the 90,000 meters, and then 1 hour is 3,600 seconds. So maybe save a step or two. It's a pretty quick way to do a conversion. In fact, you can kind of put that in your calculator. If I see 90 kilometers per hour, I can put 90,000 on the top, divide through by 3,600, and that's going to come out in meters per second. So you can kind of imagine doing those units conversions. Anyway, we ended up with exactly 25 meters per second. Now, that's a 25 meter per second increase in velocity, so that goes here, and I should have written that right here. Maybe I can add it, or you guys can add it. But the change in velocity, it went from 0 to 25, that puts 25 meters per second on top, and then the time elapsed was 5 seconds. So 25 divided by 5 gives me 5. And then what are the units for an acceleration? And the units on an acceleration are going to be meters per second, okay? And so that gets shortened to meters per second squared, but I kind of like to say meters per second to remind myself that it's a velocity, a variation in the velocity, a change in velocity, which would be meters per second, divided by a time, which is seconds. Okay, so I think, yeah, we did it all here. So it is all listed here. So average acceleration, that's going to be delta v over delta t. I'm going to write that as v2 minus v1 over t2 minus t1. I'm going to write that as a difference or a change in velocity during a time interval, a difference in time. v1 was at 0, v2 was this 25 meters per second, and the time interval was between 0 and 5 seconds, so I plugged all of that in. 25 divided by 5 gives me the 5 meters, so it's the same thing that we saw on the previous page. It looks like we have accounted for everything. And so if we're going up at 5 meters per second, then each second that goes by, the velocity goes up by 5 meters per second. Now, in this case, what they showed us was that not only was this an average acceleration, but it was actually the instantaneous acceleration, I think, because they showed the car steadily increasing. See how at 1, 2, at those intermediate times, it was still following that constant acceleration. It doesn't have to be constant, but in this example, it looks like they've set it up that way. All right, so here's a good conceptual example. Velocity and acceleration, are they the same thing? No, they're not, right? So don't get them mixed up. If somebody tells you the velocity of something, that doesn't tell you anything about the acceleration. They have to give you a series of different velocities at different times in order to determine average or instantaneous accelerations. So, for example, if the velocity of an object is 0, if an object's at rest, does that mean that the acceleration is also 0? Well, an object at rest, if it stays at rest, if it's just sitting there and it stays there, then not only is the velocity 0, but the acceleration is also 0. But in general, that doesn't have to be the case. Just because something is momentarily at rest doesn't mean it's going to keep being at rest, right? If I take this textbook and I hold it up, momentarily it's at rest, but what happens if I let go? Well, if I let go, if I remove the force that I'm holding it with and let gravity just exert a force on it alone, it will accelerate. So a good example of something that has a velocity of 0, even though the acceleration is not 0, is an object that when we drop it. So when we first let go, the velocity is 0, but the acceleration has kicked in. If the acceleration is not kicked in, what would the object do? What would happen if I had a book, it's got a velocity of 0, I let go, but the acceleration is also 0, what would the book do? And it would hover. Because 0 acceleration means the velocity is not changing. So if we throw something into the air, so what happens when you throw something is its velocity is upwards until it gets to the very top, and it's decreasing. There is a moment right at the top where its velocity goes to 0, but the acceleration is still downwards. So there is still a force acting on it, pulling it back towards the Earth, and there is still an acceleration. Again, if, when it reached the top, if for some reason the acceleration went to 0, it would hover. It would just stop at that location. And that's not what happens. The object continues and comes back. So definitely there's examples of, even if something is momentarily at rest, doesn't mean the acceleration is necessarily 0. Now, if the acceleration is 0, does it mean that the velocity is 0? And you go, well, if the acceleration is 0, it means the velocity is constant. So if there's no increase in velocity or decrease in velocity, then the acceleration is 0 for that object. So here is something, I guess it's a car, moving along with what I'm claiming to be a constant velocity. Now, if a constant velocity, then there's no acceleration. Okay. How strict is the requirement, or the requirements, how strict are the requirements for constant velocity? Now, constant velocity, we said, means the same thing as 0 acceleration. Those are interchangeable. If I say, oh, that object has 0 acceleration, that's the same thing as saying, oh, that object has a constant velocity. Now, the constant velocity could be at rest. Being at rest, consistently at rest. So it's at rest and it's staying at rest and it's just at rest. That's an example of a constant velocity. It's a constant velocity of 0. So if it stays constantly 0, then it just stays at rest. Constant velocity requires that there be a fixed speed, and that speed could be 0, but more generally, any constant speed, and it's got to be in a straight line. So to be truly constant velocity, you can't be turning in different directions. So for example, let's say I have a velocity here and I'm going in what I've decided to be the x direction. Well, what happens if I turn and go in a new direction? Well, if I go in a different direction, then my velocity in the x direction is no longer constant. So in order to have a truly constant velocity, you've got to be moving only in a straight line. Okay? Or at rest is also an example of a constant velocity. So that's very restrictive. And so again, I was kind of joking around that that's kind of a homework assignment, is practice constant velocities, but I guess I'm not really kidding. It really is good to just experience, what does it require to move at constant velocities? So I've got to keep straight line, I've got to keep the very same speed, the very same magnitude of velocity the whole time. So that's very restrictive. Now, when you think about it, this makes for a nice classification of motion. All motion that we look at falls into one of two categories. Category 1 is constant velocity. Category 2 is some kind of an acceleration. And category 1 is very restrictive. So most of the motion that we look at falls into category 2. Its velocity is changing over time. It's either going faster or slower. Again, things that are consistently at rest, staying at rest, at rest, are examples of constant velocity. We'll see that when we get into chapters looking at forces and how forces create accelerations, we'll see that these two categories are very useful to think about. All right, we'll leave it there. We'll just say that these are two categories of motion. Let's go back and think about that example of an object thrown into the air. So I got something and I threw it into the air. What is its velocity like instantaneously, and what's its acceleration like instantaneously? And let's ignore air resistance, so we'll use a small dense object. something that, or maybe a large dense object. We'll use a dense object where air resistance, this doesn't work with a leaf falling from a tree. But what we find when we throw something up in the air is that we have a constant acceleration, or what we're assuming to be a pretty constant acceleration on the object back downwards towards the Earth due to a gravitational effect. So on the way up, the velocity is upwards, but the acceleration is down. And if I've got velocity in one direction and acceleration opposite, that results in a slowdown. When an acceleration is opposite the velocity, the object is slowing down. When I get right to the top, the velocity has become 0, but there is still a downwards acceleration, and that's why the object doesn't stay there, but it comes back to Earth. Now this is on the way up, and this is on the way down. On the way down, the velocity and the acceleration are in the same direction. And anytime you have, for a given object, acceleration and velocity in the same direction, it's speeding up. Anytime you've got velocity in one direction but acceleration opposite, it's slowing down. Anytime you've got velocity in some direction and a 0 acceleration, that object is going to maintain constant velocity. Okay, now graphing it is really useful because if I start at point A, which is on the ground, and I throw this object at some speed, it's making its way upwards, but that speed is steadily decreasing as a function of time. What we find out is that gravitational forces create an acceleration on an object which is constant over short distances. The gravitational field drops off as you get farther away from the Earth's surface, but for short distances we can treat gravitational effects as being pretty constant, and that means that we'll get a constant decrease in the velocity. Now notice on the graph there's none of these arrows switching directions. If I do v as a function of time, that graph is a straight line that sails right through point B. B just happens to be at the point where the velocity is 0. But what happened is, let's say we throw this thing upwards at 10 meters per second. Then it's going to decrease from 10, and eventually at B, momentarily it's at 0 meters per second, but then the velocity just steadily continues to drop into negative values, and that says, oh yeah, that works, right? Coming back down would be a negative velocity based on the coordinate system we set up. Going up would be a positive velocity, and when I graph that, the slope of this line is consistent all the way through, and that said we had a constant acceleration. So if I did the acceleration as a function of time, the acceleration value just stays steady. Now I could have written that as negative. I added the words constant downwards acceleration. So it's interesting to see how, oh yeah, from the graph I can clearly see that just for that one moment at the top, this object was not moving. V equaled 0 just for that one instant. So graphs are great for analyzing this motion. Let's see where we are. I think this is, we have time for one more example, or should we? Let's see what we do. Let's get started on this example 2. So here's an example, car slowing down, example 2.6. An automobile is moving to the right along a straight highway. Now we've chosen, again, it's a straight highway, all these straight highways. So it's like Interstate 5 out, driving through the Central Valley. So it's a straight highway, and we're choosing the direction of motion to be the positive x-axis. So that's for convenience, that works out very well. And then the driver begins to put on the brakes and slows down. It says that the initial velocity was only 15 meters per second, so not super fast, 30, 35 miles an hour. And over a period of 5 seconds, slowed to, well, it didn't slam on the brakes, because even after 5 seconds, it probably just took his foot off the accelerator pedal and the car just slowed down. But in any case, there was we want to find out what the average acceleration was. So we're going to set up, here's a picture of the car, diagrams are great. At t equals 1, we're going to call that 0 seconds. The velocity was 15 meters per second. Now, because there's a slowdown, the acceleration is actually opposite direction to the velocity. So we're starting to use these arrows. In the next chapter, we're going to call these arrows vectors, just to give away the next chapter. So we're going to have a velocity arrow or a velocity vector in the positive x direction, and we're going to put the acceleration vector in the negative direction. And we have to handle our plus and minus signs carefully. They've decided to go ahead and put a minus sign here. That's fine. So the arrow points in that direction, and they've also put this as a negative sign, so they've done both. And during 5 seconds, we have slowed down to 5 meters per second as a result. So let's see what this is. They just want the average acceleration, right? Okay, we can do that. So the average acceleration here, same pictures as before. Velocity is one direction, but the acceleration is opposite. Here we are at the starting time. Final time was 5 seconds later. We started at 15 meters per second. We ended up at 5. To get an average velocity, or an average acceleration, sorry, delta t over delta v over delta t, and putting all the numbers in very, very carefully, difference in velocity over the time interval, delta v over delta t, and putting the numbers in, and the units. Notice I got units here. I'm going to check units first. So it's meters per second, that sounds good. So it's meters per second, those are the correct units for an acceleration. And the number we got on average for the acceleration is -2. So, so that's it. That's an example of carrying out one of these problems. Now, it says in this, on this slide, there's a difference between negative acceleration and deceleration. I think this is important. A negative acceleration is an acceleration in the negative direction, and that negative sign depends on how we have set up the coordinate system. So we could set up the coordinate system so up is positive and down is negative, or we could set up the coordinate system so down is positive and up is negative. You know, if I drop something and it accelerates, in one of those examples, the acceleration is in the positive direction, but if I switch the coordinate system around, now I've got an acceleration in the negative direction. So a negative acceleration refers to the coordinate system we're working from. Deceleration specifically refers to when the acceleration is opposite of the velocity. So a deceleration means we're slowing down. A negative acceleration doesn't necessarily mean that. So just so we're clear, and again, let's look at these. If I have something moving in this direction and the acceleration is opposite, that is slowing down. If I have something moving in a direction and the acceleration is in the same direction, that object is speeding up. Okay, so I think that's a good place to stop. We will stop right there, and then we'll pick up next class. We'll start right in with definitions of instantaneous acceleration. Any questions on any of the stuff we've talked about? Stop by office hours. Let's get questions answered. Make sure you're staying caught up. We're in chapter 2 now. This is the real stuff. So make sure that you're looking at these examples, you're looking at homework problems, and understanding each and every step.